This meeting is being recorded.
In this video, we'll continue with the discussion of section 17.4, and let's review what is the criteria for aromaticity. So what types of compounds will demonstrate this aromatic stability? They will have to fulfill two criteria. So number one shown here is that we have a fully conjugated ring with overlapping p orbitals. So what that means is that there has to be a p orbital available, and whether it's carbon or other atoms involved, they all would have to be sp2 hybridized. Or else we would not have an extra p orbital available for that overlap. So fully conjugated with overlapping p orbitals, they need to be ring structures for this to occur. And the second criteria would be that they have a Huckel's rule met, or a Huckel's number, rather, of pi electrons. So this number is 4n plus 2, where n is any integer from 0, or any positive integer, right, from 0 up. So down below here, these two compounds that would meet the first criteria, they are fully conjugated rings with overlapping p orbitals. They do not meet the Huckel's rule, though. For example, in cyclobutadiene, what we see here are 2 pi electrons over here, another 2 pi electrons here, so we have a total of 4. So this is a amount of 4n pi electrons, but not a Huckel's number of 4n plus 2. Over here, we would have 2, 4, 6, 8 pi electrons. So once again, this is for an n of 2, this will be 4n electrons, so 8 pi electrons, that's not a Huckel's number either. So both of these would be considered not to be aromatic compounds because they fail the second criteria. So we can explain this Huckel's rule if we take a look at cyclobutadiene from a molecular orbital theory perspective. So we want to consider these molecular orbitals for cyclobutadiene, and we note previously that there are 5 pi electrons, and this is what we see here. All of these p orbitals that are available on each of the carbons here are overlapping, and we see that we have a fully conjugated structure. But what we see here are that we lack a closed shell electron configuration. So that would be having paired electrons in both of these orbitals here. The psi2, psi3 orbitals here, they have those unpaired electrons, and they are therefore in these non-bonding molecular orbitals, and we would call this compound, as a result, anti-aromatic. So it qualifies under the first rule, but it fails the second, so it's anti-aromatic. With cyclooctatetrene, we see something very similar. We see that these 3 lowest energy bonding molecular orbitals have paired electrons, they're full, but we see these 2 unpaired electrons here in a 2 different non-bonding molecular orbitals. So once again, this would suggest this compound be anti-aromatic. And we can also say that this structure would not be aromatic, would be anti-aromatic, because of the structure which it adopts, this tub-shaped conformation, because of other steric factors, it would avoid being aromatic. So another way to quickly, or simplify rather, our determination if something will be aromatic or anti-aromatic, we can take a look at using this process of Frost circles. So we can predict the relative molecular orbital energies and then start filling these orbitals to see if we would have an aromatic structure. So step 1 is always to draw a circle. Step 2 would be to inscribe a polygon inside of the structure, so the shape of your cyclic conjugated structure inside. So this one here has what, 1, 2, 3, 4, 5, 6, 7. This is a cycloheptane here. And we would draw a horizontal line at each point. Also, we have to note that at the bottom of the circle, one of the points of the polygon is pointing down. So once we have all 7 of these points with molecular orbitals drawn in, you can erase the polygon inside, and we have this dividing line in the middle of our polygon already in place, and we can see that the bonding molecular orbitals are below that dividing line, and anti-bonding molecular orbitals will be above our line. So again, we can quickly see here that frost circles can help us explain this 4n plus 2 rule if we were to place our polygons inside of these frost circles. We would always see that we would have an odd number of electron pairs. So we have one bonding molecular orbital here. We could have one electron pair in our lowest energy. If we have 3 bonding molecular orbitals with this 5-membered ring, we could have 3 pi bonds within, and like so. So 6-membered rings, right? This would be our benzene. Then we have even 7-membered rings, still have 3 bonding molecular orbitals. So the keynote here is that aromatic compounds will always have an odd number of electron pairs.